we shall be discussing a free body diagram, a few cases and a few body diagram. So if you need to discuss free body diagram, these are the steps you'll have to follow. Let me outline the steps. First is isolate the body, for which you are trying to sketch a free body diagram. Okay. Then find the contact points, whatever they are, find the contact points. Then determine the direction of force. And finally, you can label the force and also see if it is balanced or not. So we will take a few scenarios and discuss. Let me go to the first scenario. This is the simplest. Egg falling from the nest, or you dropping a ball. You can take whatever. So when this egg is falling, sorry, that was very lousy of me. Let me take an egg falling from a nest. So there is nothing pushing this egg, right? What is acting on the egg that is bringing it down? That is the gravitational force. So there is only one force that is acting on the egg, and that is force of gravity. This is the simplest of cases. So you can isolate the egg and see what is acting on it. Obviously, it is only gravitational force that is acting on it. Let us go to the next scenario. Block resting on a table. So let me just roughly sketch this. And maybe a block resting on a table. This block is resting on the table. So now let me forget this table and let me draw only this block, right? Let me draw only this block. Now having an object, obviously we know that force of gravity will always act on the object. So what is the force of gravity trying to do here? The force of gravity is trying to pull down the box, the block. But we know this block is not falling down. Why is the block not falling down? Because there is a table underneath it. And how does the force of the table act? It's a normal force which is acting perpendicular to the block, right? So this table exerts a perpendicular force on the block and pushes it upwards. We call it a normal force. And how is this normal force acting? This normal force is acting upwards. So we know this normal force is equalizing this force due to gravity, and that's why the block is stationary. The block is not moving, right? Let us go to the next scenario. Block on a table moving with a constant velocity. So okay, now I have a table, I have a block. This block is moving with a constant velocity, right? Velocity is constant. Let me recall Newton's first law here. Everybody continues in a state of rest or of uniform motion along a straight line unless acted upon by an external force. Uniform motion along a straight line. So this block, the fact that it is moving with constant velocity obviously means there is no external force acting on it. Newton's first law, body continues along a line in uniform motion unless acted upon by an external force, which means there is no external force acting on it and the body is moving with a constant velocity. Now let us isolate this block. As we have already seen, there is the force of gravity that is acting downwards. There is this normal force. Remember, normal force always acts perpendicular to the surface. There's a normal force that is acting upwards. There is no applied force, but this body that is moving with a constant velocity is not gathering speed because of, yeah, because of frictional force which is offered by the stable surface. This body, this block, is moving in this direction with a constant velocity. So, what is happening? The frictional force is acting in the opposite direction so as to balance this velocity. So, what will happen? You have a third force, which is a frictional force acting on the body. This will be the free body diagram for a block on a table moving with a constant velocity. Let us modify this a little more. Now, a block on a table accelerating. So, what do I have here? I have a table. I have a block. This block is accelerating. So, what is happening? The velocity keeps varying. The velocity keeps increasing. When will the velocity keep increasing? When there is an applied force which is working on increasing the velocity. So now we have a different scenario again here. So if you take here, these were balanced. If you take here again, this was balanced and the frictional force is trying to balance the velocity. They are all examples of Newton's third law of motion as well, wherein the statement goes like every action has an equal and opposite reaction. Like here or here, a reactant force trying to impede the motion of the block. Now let us take this case. So you have a block, right? You have a block here. Let us go with the things we already know. Force of gravity acting downwards. Then we have a normal force which is acting in this direction. Fine, that's done. So what do we have here? We have the block that is accelerating. So what is happening? There is a force that is trying to accelerate the block. Let us call it an applied force, some FA. But what is happening here? There is a frictional force which is acting against, failing which the block is going to accelerate madly. So there is a frictional force, but again, since the block is accelerating, this applied force obviously is greater than the frictional force, which means you have a scenario here where F applied is greater than F frictional, which means here you have a case of Newton's second law. Force is equal to mass into acceleration. In the case of an unbalanced force, you have this case of Newton's second law, where force is equal to mass into acceleration. So we have seen a few simple cases. Let us go to more cases. A gymnast is holding on to a bar, suspended motionless in air. So what is happening is, there is this bar. Okay. Gymnast is holding on. The bar is attached to two ropes attached to a ceiling. So what happens to this bar? This bar is attached to two ropes attached to the ceiling. Okay. So this fellow gymnast is probably holding on with his two hands. Let us take him as an object which is suspended here. Okay. Take him as an object suspended here. So again, let us isolate the gymnast as one entity. When you take gymnast, it's one person who's holding on with his two hands. There is this gymnast who's suspended here. So now, what are the forces acting on the gymnast? So this is an isolated person. There are 2 points of contact here. So what happens to these point of contacts? They go up. These point of contacts go up. He is pulling up. The point of contacts is pulling him up. So what is this force called? This force is called Ft, or you call it force of tension. Force of tension which is acting upwards. I'm sorry. This force of tension which is acting upwards, he's pulling it up. But why is he not going up? Of course, you all know the reason. He is not going up because the acceleration due to gravity. Now see, bar suspended motionless in midair. Motionless, he's just hanging there. There is a tension force or force of tension. Force should be equal if the material is same, or you can also say his hands. So tension force acting upwards, and there is a gravitational force which is acting downwards, balancing each other. You can say the same about your bag. When you suspend your bag on your shoulders, if there are two shoulders, if you suspend them on both the shoulders, you have two cases of force of tension. If you suspend them on a single shoulder, again it's a case of tension against. To another similar scenario, a car, a similar scenario to the earlier one we have seen, not the previous one. Car is moving to the right and slowing down. So let me again recall the case of a block. So when you speak about a block, when the block is moving in the constant velocity, uh, there is no applied force and so on. Here, car is moving to the right and slowing down. See, I think most of you who are looking at it would have either used a cycle or a bike or a car. When you are slowing down your bike or a cycle or a car, you will stop applying any acceleration. Am I right? If it's a cycle, you'll stop pedaling. If it's a car or a bike, you will stop giving acceleration, which means here the applied force becomes zero. There's no applied force. So you have the road, you have the car, sorry, you have the car that is moving, right? This car is moving, but it is slowing down. It is slowing down means the applied force. The applied force is not there, is equal to zero. So now you're isolating the car. What are the forces acting on it? Obviously, number one, there is a force of gravity which is acting downwards. These are default forces. There is a normal force exerted by the road on the car which is acting upwards. There is no applied force. Now the car is slowing down. Why is the car slowing down? Because there is a frictional force which is acting in the opposite direction. Remember, normal force is always perpendicular, frictional force is always parallel. So there's a frictional force which is acting on the car that is slowing down. Free body diagram for a car that is slowing down, not for a car in not for a car that is accelerating. I think you can equate it to those blocks, right? Now I have a scenario like this. Okay, I need to draw the free body diagram for mass 1 and mass 2. So let me again, as I told you, let me isolate each mass. So if I have mass m, m1, is there any force here? No. I do have a force of gravity acting downwards. It is on a table, which means I have a normal force acting upwards. As I told you, I have isolated the object. And what is in contact? Number one contact is this one, which is exerting a normal force upwards. A force of gravity is always there. What else is there? There is a string here. There is a string that is trying to pull this mass in this direction. So, what is this? Tension force. Okay? A reaction force, a tension force that is trying to pull this mass. If I'm going to draw a free body diagram for M2, okay, let me draw a free body diagram for M2. What are the points in contact? I don't find anything here. I don't find anything here. Obviously, there is a gravitational force that is pulling it down. And you see there is a string here. What is this doing? It is pulling it up. Force of tension. This is a free body diagram for M2. Assuming the whole system to be in equilibrium, if you draw a free body diagram together for these two, this Ft and this Ft, sorry, this is F, right? This Ft and this Ft will get cancelled, which means you will only effectively have this normal force, gravitational force, and a gravitational force. Okay. Okay. So that is it for this one. Let me see if I have any more. Yeah. I have a weight suspended by a thread. So what are the forces acting on this? Obviously, okay, if you're going to isolate this, wait. Number one, you all know That's the force of gravity acting on the weight. If it is the same thread that is going through this, so what will I have? I will have Ft both acting, of course, inclined but upwards, which is counteracting this Fg. If I have two different threads, I may have Ft1 and Ft2, which may or may not be equal. This is also a simple case. Now, let me take the case of this one. So, I have a mass m here. I have a mass m here. Let me call this first ball and let me call it a second ball. Let us isolate the first ball, right? Ball 1, right? Now, easiest, force of gravity acting. Is there a normal force here? No, there's no normal force here. Where is the normal force? There's a normal force here. And what do I have here? There is this ball, and how is it acting? It is acting in an angle to ball 1. So what is happening? I have a reactive force here, some reactive force here, which is keeping the ball 1 on top, right? Now, what about ball 2? I have ball 2 here. Okay, sorry. So, M or Fg, you can say W is equal to M into G. This is the weight which is acting downwards. That is what it is. Similarly, here you will also have W is equal to M into G, which is the force due to gravity. Okay. And, or, okay. Now, this mass is trying to push it down. We all know this. Now, let us see what are the other forces. Here, there is a normal force. Am I right? There is a normal force here. And what is the force I have here? There is a reactive force which is acting downwards. A reaction force which is acting downwards. So this is the free body diagram for ball 1. This is the free body diagram for ball 2. If I draw the free body diagram for the entire system, this Fr and this Fr is going to get cancelled. If I consider it as a single system. Am I clear? Right. Now, this is a free body diagram for a plank which is attached here. Now, when you see this here, what is happening here is there is a gravitational force always that is there. But what is happening here is this plank is not allowed to move this way or this way. So, what is happening? There is a plate force here. This can vibrate this way, but this plank is not allowed to move this way or this way. And then if there is a support here, suppose this same plank has a support here, apart from a force here, you will also have a force here which is acting upwards, counteracting this force due to gravity. Right, let us come to this scenario now. Okay, now coming to this scenario, what do we see here? We see a block A, we see a block B here. So this is at an angle 30. They are connected to this post. This is a post. Okay. By two strings T1 and T2. T1 and T2. Now let us take the case of A. Case of A. So what do you have here? You have a gravitational force that is acting downwards. Am I right? You have a gravitational force that is acting downwards. Now this is at an angle 30 degrees. So to the vertical, to this surface, what will be the angle? This will be 60 degree because here it is 30 degree. You have a gravitational force that is acting downwards. What is the direction of the normal force? See, this is the surface, right? So the direction of the normal force is this, perpendicular to the surface that is holding. Apart from this, you have this block B, which is acting this way. Are we done? Absolutely not. You have a tension force that is holding on to it. So you have a gravitational force which is acting down at an angle. You have a normal force which is acting perpendicular to this, and you have block B exerting a force downwards. So what happens to block B? As far as block B goes, you have this force that is acting downwards. You have this A, normal force that is acting like this, right? Normal force which is acting on top. You also have Ft, which is acting this way. This is the direction of the force we all know. It's Ft, which is pulling it this way. What happens to the post? To the post, you have T1, which is acting like this. You have T2 acting like this. Let us call it some P, which is holding it up. Some force P, where P is equal to T1 plus T2. So this is a free body diagram for the post. I think this is the last one, if I'm right. Yeah, this is the last one. So I have two surfaces inclined at an angle alpha and beta respectively, and they are holding this together. Now let us isolate this body. I'm isolating this body. I will have a force of gravity that is acting down. Now, this is the surface. I told you normal force acts perpendicular to the surface. So, what is the direction? This is the direction. So, this is the direction of the force here. Here again, normal force, this is in contact. Again, normal force acts perpendicular to the surface. See, this is perpendicular, right? So that's why I've drawn it here. Similarly, here also, there is a normal force that is acting perpendicular to this surface. At what angle? If this is going to be alpha, then this angle to the vertical is also going to be alpha. And similarly, this angle to the vertical is going to be beta. This is how you deal with inclined levels. So if there are any more doubts in free body diagram, if you want any more scenarios dealt with, reach out to me. Okay.